So I have a few homework questions here on Piazza, so let's see if there's something useful I can say about them. So here someone said, would a vertical bar be added if Louise had a child? I guess that depends on whether it's a legitimate one. So if Louise had a child, then this part here would look like this. We would have Edward, then Louise, Bristol, and here we would have Severn. And so the answer is yes. So here there would be that vertical bar, which I guess the person was asking about. And so the way this works is that when Edward asks Louise to print herself, Edward says, since you're not the last child, when you print yourself, just be sure to use that vertical bar in addition to the stuff that came in front of me, which was what? Which was a bunch of other bars, whatever. Edward doesn't even know. He just takes what was handed to him. And then when Louise prints herself, she says, I'm going to completely ignore those last three characters. I'm going to print the plus, minus, minus, this part here. But then when Louise asks Bristol to print herself, she's going to give this entire string, including those vertical bars, to Bristol. And she's also going to tell Bristol, and when you print yourself, okay, how should Bristol print herself? With or without vertical bar? Without, since she's the last and only child. So Bristol is told, don't use vertical bars. Bristol is going to ignore that advice and instead put them plus, minus, minus, but she's going to pick up the vertical bar that she got from the parent. So it'll all. Does that answer this question? I hear stony silence. Now over here we say, is this one correct to print? And so when I have a look at it, I can immediately say no, because look, there's a bar missing here. There is a plus, minus, minus missing here. Oh, actually, I don't know which one this is supposed to go. Hang on, let me erase this. I can't parse. No, I think this bar here shouldn't be here. Oh, I see what's happening. It should be over. Come on, silly thing. This bar should be over here. So the answer is no. All right. I mean, when you look at it and you see some solitary bar there in the wilderness, you know that the answer has to be no, right? Okay. When you're printing out Louise and Severn, there's no way for you to know that there isn't another subtree. So the parent does not know how deeply its children and grandchildren nest. It doesn't. All the parent is responsible for doing is to tell all but the youngest child to use the vertical bar and the youngest child not to use it. Then what goes on in further recursion levels, the parent has no control over that. That gets built up by the children that later are the parents of the grandchildren. So the parent really does not need to worry about anything except whether for its own level there is the bar. So in a way, all of these parents and grandparents and children and grandchildren collaborate. Each of them is responsible for one slice. And so a node is only responsible for that slice of stuff that happens under itself. So if you look at a typical tree here, like if you look at this this tree here, and we'll look at, say, Elizabeth II. So all she's responsible for is that this stretch of stuff here happens correctly. And so she has to signal to Charles, Anne, and Andrew that vertical bars must be there, and she has to signal to Edward that they must not be there. That's all that Elizabeth II worries about in life. And she gets paid a handsome income for that, and a castle and all that. So, question?
I still don't understand when we are not printing the bar. Not how to do it, but when the vertical bar is not printed.
Okay, the vertical bar does not get printed. Like when Louise comes along, what she gets as the prefix. So let's look at Louise's prefix.
I couldn't just dispense with the prefix stuff just if we were just to look at a tree. You know, like the tree you have in the book.
Yeah.
When does the vertical bar not get printed?
Well, see, let me print it. Let me just draw it by hand. By hand, you would draw the thing like this, right? So this one would be child 1, child 2, child 3, child 4, child 5. You would draw a vertical line that extends all the way up to child 5, and afterwards, here you don't want to draw it anymore.
And why is it?
Just because that's how you would kind of draw the descendants. There are no further descendants, so there's no need to have a vertical line. And if you did continue to draw it, it might interfere with other stuff. See, there might be some other subtree coming further down here, and now if you simply continued it all the way through, then it would be hard for someone to see where one subtree starts and one subtree ends. So you really do want to have that gap. So if over here, if I simply filled in vertical bars everywhere, it would look very messy. So they do have to stop somewhere.
So if it's the last child, then you do not print the vertical bar?
That's correct. So, and the thing is, it's not that you print it, it's the child who prints it. Right? So you need to tell your child, don't print vertical bars, because you're the last one.
Okay.
And so the reason that I use the prefix is that it nicely accumulates all of the decisions. You know, one could equally well pass like an array of trues and falses. And I haven't actually thought this through. Could you ever have a situation? Yes, you could. I mean, just to make everyone really unhappy. So in the situation that we just talked about here, where Louise has, come on. Here, where Louise gives birth to little Bristol, then you have this interesting situation. You have a vertical bar, you don't have one, just a space, and then you could have another one here. Right? So you could have any patterns of have or have not in an arbitrarily complex tree. But as always with recursion, the best way to think about it is not to think about it. So you you just want to think about what does the parent tell its child? What does the parent what is the parent told by its parent, and just work with that.
And so if it's the last child of a parent, it never prints the bar.
It never prints the bar under the parent. I mean, there may be bars coming in from the left. See, if you look at this particular line here, that here there's some bars from the grandparents and great grandparents, but here there is no bar. So that is really why it is useful to think of the prefix. The prefix is like the accumulated history of all of the ancestors. Each of them says, print a bar under me, don't print a bar under me, print a bar under me. The parent augments that and said, take the wisdom of the ancestors, and also don't print a bar under me.
So you pick the prefix, and if you're the last child, you do not print a bar. If you are
Yeah. Now notice that you add something. You still add 3 spaces to the prefix. It's not that you add nothing. That might have been the problem of this person where there was like a bar in the middle of nowhere.
Now, when do you add the prefix?
you add this. You add one of two things. You add the vertical bar and 2 spaces if you want a bar, or you add 3 spaces if you don't want a bar. So either way, you add 3 characters to the prefix. Right? Yeah. So if you add things, if you forget to add those 3 spaces, then you do get the bar in the middle of nowhere. Now, the Lord knows that whenever I'm in the middle of nowhere, I wish I had a bar, but that's not the same thing. So, yeah, so the other thing, like I said before, is that when someone prints themselves, they do have to print this segment here, the plus and the minus minus, and that overrides whatever they got from the parent. So you have to rip out the last 3 characters just in that stage. And I guess people have gotten that all right looking at what they've produced here. And then finally, something funny happens in the very first position where, like, George doesn't print anything in front of himself. And one of you posted something saying you dealt with that by sensing that the prefix was 0. That was the empty string. And then that's the right idea. All right. I realize it's a tricky exercise. I don't know if I told you. I fondly remember when I did this when I was an undergraduate student, and so I felt you should share in that experience. Homework 10C. If the root is not null. So the question is, if you had a tree that was completely empty, how should it be printed? You shouldn't print anything. So you should simply say if the root is null, just don't print anything. I don't think I'm testing it, but that's the obvious way of dealing with it. Okay, more about homework 10C. Okay, so I think we're good for now. So if you have more questions, put them on here. Okay, so today's lecture is about Huffman coding, mostly because it's kind of an interesting application of binary trees, and also because the priority queue enters itself in there, and so it's the one situation where you might actually see a priority queue in action. So when you have a Huffman tree, it has this characteristic shape that the leaves have symbols, which could be letters or colors or whatever. So here are the letters. And the interior nodes do not have any symbols. They're blank. Whenever you go to the left, that means that you want to emit a code word of 0. Whenever you go to the right, a code word of 1. So the letter K, for example, is encoded as 0, 1, 0. And so the letter P over here, you'd have to find the path to the P. 1, 2, 3, 4, 5, 6. So that would be whatever. 1, 1, 0, 0, 1, 1. So you can see it's a variable length code. Some of the symbols have longer codes than others. And so, of course, one wants to do it in an optimal way so that frequent symbols have short codes. And let's see why that's the case here. So I've chosen not the English alphabet here because that makes the tree kind of big with 26 symbols. So it's the Hawaiian alphabet apparently has, 13 or 14? That's right, 5, 4, 5, 6, 7, 9, 10. The Hawaiian alphabet only has 13 symbols, one of which is that funny quote that I don't know how to pronounce. And so apparently the letter A is the most frequent character in Hawaiian, which, given how often it occurs in the word Hawaii, seems believable. And I guess the I should also be kind of frequent, but looking at this one here, maybe the O is actually more frequent because the O has a somewhat shorter code word. So I computed this by getting somewhere from the internet some statistics of letter frequencies in Hawaiian, a language with which I'm otherwise not very familiar. So I'm just taking their data on faith. And they said what the frequencies were for each letter. And then I built the tree using that algorithm. All right, so the most striking characteristic of this code is that no code word is a prefix of another. So if you look at the code for K, the 010, no other code word starts with 010. And that's important because when you have a long stream of zeros and ones, there are no spaces in between. It's not like Morse code where you would have spaces in between the code words. You just have this infinite stream, or a long stream, presumably finite, this long stream of zeros and ones, and now you have to know where to stop coding. So the way it works here is you go 0, 1, 0, that gets you to an endpoint, and you say, okay, that was a K, and now you go 1, 0, that was an A, and then you do 1, 1, 0, 1, and that was an E, and then you go 0, 1, 1, 0, and that was a U, and then 1, 1, 1. I guess I should put another one, another thing here. And then you put an N. That was probably an unfortunate choice because I'm sure that means something very bad in Hawaiian. But there you go. So even though it's a variable length code, since no code word is a prefix of another, you can decode it unambiguously. If we had symbols in the middle, if there was another symbol here, then the prefix property would be violated and decoding would be much more difficult. All right. And I'm sure I have a clicker question. Yes, indeed. All right, so code away and tell me what's the encoding of the one Hawaiian word that I do know. All right, so let me work on this while the remaining answers come in. So A is here, so that's 1, 0. L is, it's over here, 0, no, 4 zeros, 0, 0, 0, 0. O is here, 0, 0, 1. H is 0, 0, 0, 1. And A we have again. So if I string them all together, I get 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0. Okay. Oops, and now it went away. So I have no idea which of those options there was. So let's hope that you guys know. So everyone says it's number 2. Sounds believable. All right. All right, so that's fairly straightforward. Do I have a decoding question? Oh, no. So some codes are Huffman codes, and presumably some codes are not Huffman codes. And so I'd like to know which of these is not. And if you don't know, just guess. I figured that, particularly with UTF-8, you might not exactly know what it is. Just give it your best guess. There's no penalty for a wrong guess. All right, so let's look at Morse code. Now, so in Morse code you have long and shorts. So like a lower in Morse code would be like that. So you could say a short is a 0 and a long is a 1. And so it sounds like, it's a binary code, but actually Morse code is not really a binary code. Why not? Yeah, because you have the spaces in between. In order to be able to decode Morse code, the spaces are significant. So when you hear a short long, and then there's a space afterwards, then that's an A. But if you have a short, long, short, that's an R. I don't expect you to remember that. I just learned that when I was like 16, and you never forget. So the spaces are significant, and so really Morse code is a ternary code, a code with 3 symbols, long, short, and space. And so therefore it can't be a Huffman code. So it's not. What about 7-bit ASCII? So I hope you have an intuitive idea what 7-bit ASCII is. It has the various letters, the various numbers, and it associates a 7-bit code with all of those 128 possible symbols. It doesn't encode everything. It doesn't encode characters with accents or Chinese characters, but it encodes these 128 characters. Is it a Huffman code? And the answer is yes, and it's a Huffman code with a particular structure, namely that the Huffman tree is the complete tree. I can't draw it that fast. It's the complete tree of length of height 7. And so at the very end, you have the various code words, like for NUL, all the way up to, so you have the control characters, and you have somewhere you have A, B, C, and so on. They're all at the same level. So kind of technically it's a Huffman code because no code word is a prefix of another. But non-technically you could say, well, it's not really a Huffman code because they all have the same length, even though an A is surely more frequent than an X. So in that sense, it isn't. And so if you were to say it's not, that would be a rational argument too. So just from its shape, from its structure, it's a Huffman code, but it doesn't fulfill the intent of the Huffman code that each character is equally likely. So what about UTF-8? UTF-8 is not a fixed length code, unlike ASCII. Some code words have 1 byte, some of them have 2 bytes. You can go up to 4 bytes. And it also has the property that no code word is a prefix of another. So it is, technically speaking, a Huffman code. And there it is kind of true, at least for English, that the more common characters, like the Latin characters, they have shorter encodings than some of the less common ones. So let's see how people felt about this. And so most people said Morse code is not, and some people said none of them are. So I think the ones who said ASCII isn't should think about it. Or no, maybe not. I mean, so in this case, there was no wrong answer. But I think the technically most correct answer is Morse code is not, and technically the other ones are, just with strange frequency distributions. All right, so now I want to build a good Huffman tree. Not just any old Huffman tree, but one that optimally encodes. So here is and I wanted to not just use letters because it's kind of boring. So I said, let's use it for colors. We can encode colors. So here is a charming drawing that one of my daughters did about a year ago. And so most of the pixels are white from the paper. And so apparently she had an orange pen and a pink pen and small amounts of yellow and blue and greens with these percentages. And so we want to encode each color as a string of zeros and ones. And this is actually more practical than you might think. When you encode a graphical image like a photo with GIF encoding, it uses essentially this scheme. It builds a Huffman tree and uses it for encoding that image. Every image has its own encoding. So we want long codes for the rarely used colors like green, short codes for the popular colors like white. So this fellow Huffman had this problem, realized that this was a problem that needs to be solved when he was a graduate student, and he just solved it. So he came up with an algorithm that builds this optimal tree. And it's not actually a difficult algorithm once you think about it. Gosh, let me make this bigger. I can't. Okay. So he said, we're going to add all of the nodes to a priority queue, and we're going to be sorting them in the priority queue by the frequency with which they occur. So, see if I have the frequencies here. Well, I guess you can see the frequencies here. So I would make a node for white, for pink, for each of those 6 colors, and with the frequency, which would mean that blue and green would come out at one end of the priority queue. And then I would take out the nodes with the smallest frequencies. If you remember how priority queue works, it gives you the elements with the highest priority, like priority 1, priority 2. And so that would in this case be the ones with the smallest frequency. You pull them out, so it didn't matter in which order you put them in. And you make them the children of a parent. Let me draw the picture here. So now I have the one with 2% and the one with 3%. I now make a parent that says the aggregate of these two is 5%. And now this parent is again a node. I had a priority queue of nodes, so I stick that parent back into the same priority queue. It'll fall in there somewhere. Eventually, I'll be in a situation where my priority queue has only one element left. That element is a node, but of course it's going to have lots of children. That's my final tree. So let's play it out. So here's my initial queue. Now, as I've just already shown you, these are the two lowest ones. I stick them back in. We take out the two with the lowest and combine them. That gives you this tree here. We repeat this again. So in this case, we're taking out these two. So 20 and 10% adds up to this 30%. And then here you see the 20% child and this 10% child. And now notice it's a priority queue. So in the priority queue, this one now falls somewhere in the middle. The priority queue doesn't have to keep it exactly sorted, but it certainly could. It just has to make it so that when we pull them out, that the least priority one or the highest priority ones come out first. So in the next step, we take the 20 and 30 and combine them. Here's the 20 and here's the 30. It doesn't actually matter which one becomes the left and which one becomes the right child. And that adds up to 50. In the final step, we take the last ones that you see here, and they add up to 100%. We're done because now there's only one node left over. So that's the algorithm. It's actually quite simple. We're not going to discuss exactly why it gives you the optimal encoding, but it's kind of plausible that it does, because what it does is it groups together the rare ones, and because they are formed first, they end up at the bottom of this tree that gets built up over time. And so they like to have the longest encodings. So rare ones have a long encoding, and by the same flip side, the ones that get left over and untouched for the longest time are the ones that are pretty common, and so they will end up with shorter encodings. But it's optimal in a sense that one could actually make very tangible. So after the tree has been constructed, the frequencies are actually no longer needed, so one can discard them. And yeah, also I should notice that, so this is not a code for encrypting. These codes are not there to make it impossible for someone to read your messages. It's a code for fastest transmission, for using the minimum number of bits to transmit a particular set of data. So when you look at this example here, notice the prefix property, white is 0. Notice that none of the other code would start with 0. Orange is 1, 1. Notice that none of the others start with 1, 1, and so on. So implementation is pretty straightforward. The node class implements comparable so that I can put it in a priority queue. Remember, the priority queue holds node objects, and a priority queue has to hold comparable elements. In this situation here, I used, instead of using percentages, I used the actual counts, and I don't remember why. I think in the data set that I had the actual counts, and I didn't feel the need to convert them to percentages, because all it matters is which one of them, it doesn't matter that they add up to 100, as long as they are proportional to the frequency. The tree constructor gets that information, which characters are the most common ones. And so in this example here, I'm back to characters, not to colors, just for simplicity. So in the implementation, I go through all of the characters. So I have a table that says, back in Hawaiian, that A occurs in this text 1,300 times, and L occurred 930 times. I'm just making these up. And so now for each of those in the key set, I make a new node. I say that's the node for this character. I append the right frequencies. I add them to the priority queue. Then I go through the priority queue as long as I have at least 2 elements in it. I pick the smallest and the smallest one again, because when you remove one, then the next smallest is the next smallest. I make a new node, and that new node has two children, namely the smallest, the next smallest. Over here, I add up the frequencies. That's what you see here. So I take the sum of the two frequencies, and then I take this node and just add it to the priority queue again. That's all. When I'm done, when the priority queue has size 1, then the root node is the one that's the last one left standing, and I remove that. So that's all. Okay, just one question to see that the implementation is clear. So the node class must implement the comparator method because I want to be able to compare nodes. And so I'm asking you which of these implementations is the right one. All right, so if we look at the picture here, so we wanted the priority queue so that the elements with the smallest frequency are the ones that come out first. So it didn't depend on what was in it. It doesn't depend on the color in this picture or in our situation on the character. So that rules out these two. And so now we need to figure out which of the two it is. So we're computing the difference, and so comparator returns a negative value if this should come before other, and a positive value if this is after, should come after other. Now what does it mean to come before? So now we need to remember in Java the priority queue, does it first give you the smallest element or does it give you the largest element when you remove? And it gives you the smallest element, which is maybe a little unintuitive because the priority queue should give you the one with the highest priority, right? But when we say priority 1, priority 2, priority 3, the smallest number is the one that has the highest priority. So we want to make it so that small percentages or small frequencies are in fact smaller than large frequencies, and so that is choice 3. So that step always takes me a bit of reasoning through. Let's see how you guys were doing. Wow. Could have saved myself a bunch of talking. All right. So, decoding is very straightforward. Once you have the tree, the decoding works as follows. You have as an input a sequence of zeros and ones. And so you have the root of the tree. When you see a 0, then you take the node to the left. That's the code here. If you see a 1, well, if you don't see a 0, then you move to the right. Eventually, you get to a leaf. So I'm checking here whether it's a leaf by seeing does it have a left child. These trees have the shape that you either have 2 children or 0, so that's enough. And in that case, I'm done with encoding a particular substring. And so I'm taking the character that I found there and I add it to the result. And then I climb back to the root to decode the remainder. So this way I can take an arbitrarily long string of zeros and ones and decode it. So it's pretty simple. Encoding turns out to be a little more tedious. So let's go to a particular Huffman tree like the Hawaiian one here. And let's say I built this one. So this one actually was the one that was built from the actual frequency table. And now how do I encode? So I want to encode aloha, or can I encode beer? No, there's no R in Hawaiian. That would actually be a problem for them, I guess. So aloha. So now I would have to find the A. How the heck am I going to find the A? That sounds like an expensive operation. I would have to go through the entire tree, look at every conceivable node, because there's no way a priori to know which one it is. And so I would have to visit n elements in this tree just to find it. And then I would have to find the L. Again, how would I know where the L is without looking at every conceivable leaf? And eventually I would find it like all the way here. So that doesn't seem like an efficient way of doing it, particularly the second time that I want to encode the A. You know, it seems senseless to do the work again. Instead, what you want to do is you want to just do that work once and then remember it. You might as well just make a table that contains all of the letters and the encodings and compute that table once and for all. So for encoding, there's no benefit of the tree. The tree is there to give you an optimal encoding, but once you have that optimal encoding, you don't actually want to have to relive it every time. So the way that the encoding is done is it makes a map and where it computes the encoding as it goes along. So let me show you how that map is made. So you start out with the empty map. So somewhere here I have the empty map. Now I go to the left and I remember a prefix of 0. And I don't find anything, so I go to the left one more time recursively, and now I have a prefix of 0, 0. And now I go to the left one more time with a prefix of 0, 0, 0, so sorry, 3 zeros. And now I finally get some characters here, so I can say, oh, an L was 0, 0, 0, 1, and H was, no, sorry, 0, 0, 0, 0 was 0, 0, 0, 1. And now, recursively, that's a little hard to draw here, so I'm done with the left subtree here. Now I pop out back here, and I say, oh, and oh, I've now found the prefix was 0, 0, and I have a 1, so it's 0, 0, 1. So in this way, you can eventually fill up that map, and it's a data structure, it's a map, and you just keep it forever. And at that point, when you need to do encoding, you just look it up. So if I have to encode an H, I just look it up from that one-time computational path. So there's an initial path where I store the encodings of every character. No, there's only a small number of them. And then I keep that in the table. That's the optimal way of doing it. That's the way I did it in the book. So in the book, I have a map from each character to its actual encoding. That sounds like maybe it's working a little too hard. It would sound intuitively easier to have a map from each character to the node in the tree. See, if in this tree here, I had a map, where is it here? If I had a map that says L, and then it would have a pointer to over here, and W, and it would have a pointer to here, and A, and it would have a pointer to here. That sounds like that would be an easier map to build, because I could in fact build it like when I make the nodes, for example. So take that thought and now tell me, if we followed this strategy for decoding, having a map from each character to the node, what else do we need? And so I give you two options. I say, I would also need a link to the parent. And I say, I would also need in each node an instance variable that holds the code, as opposed to putting the code in the map like I did in the book. And so I'm asking you, will either of these work? Neither, or no, just one or just the other? 4 options. All right, so that's a bit of a sophisticated question. All right, so let's look at the first idea. So let's say that we have a pointer to the parent. So the L would have a pointer to its parent. So we have pointers going all the way back. So now I see an L, I find the node, and now how could I find out what the encoding for it is? So this would actually work, because I could go to from the L to the parent, and now how do I know whether the last one is a 0 or a 1? Well, I can compare, is the pointer that I have to the L, is that the same as the left, or is it the same as the right? And I can check that. They're both object references, so I can check with equal whether it's one or the other. And so if it's the left, then I know my last character in the encoding was a 0. And then I can go up to the parent again and make the same determination. Was the node that I was it on the left or on the right? And so this approach will work. If the tree is built so that you have parent pointers, then you can do encoding in this kind of simpler way, kind of ad hoc. Now, what about the other idea where I say that each of these nodes stores its encoding? And the question is, how does it get initialized? And that'll also work because when you remember how these nodes were created. So this particular, let's take this one here. This particular one here was created by gluing together, well, actually, no, how is that going to work? I take it back. So, so let's say L has a field for the encoding. H has a field for the encoding. How would I set it? So when L and H are pulled out of the priority queue, and then now given this parent, I don't yet know the encoding of that parent. I only know that much, much later when the tree finally builds itself. So I think that one can work. So I respectfully disagree with the majority answer. Let me see how I worded the question, whether I worded it wrong. See, the key phrase here is to set the encoding when the node is constructed. And you just don't know it yet when the node is constructed. You have no way of knowing at that time what the encoding will be. So you'd have to set it at some later point. You could set it with the recursive algorithm at some later point. So the correct answer is 1, which no one got. Oh my. All right, so I put up this question because it raises this whole issue of kind of the design freedom that you have when you design an implementation. And it has nothing to do with Java or C++ or direct programming, but with how do you implement a complex algorithm. And it's the kind of thing that computer scientists worry about, where computer science is more than just the programming part. All right, we have a brand new and exciting lab. It's so new that I didn't have time to fill in the learning outcomes, so I assure you there will be some. We just don't yet know what they are, but it's about scripting. But before doing the lab,